Hi, in this session I'm going to discuss data center bridging. I'll provide an overview and an introduction to what data center bridging is, why we use it in the data center, and how we can actually configure it on the CX switching platform. So let's go ahead and get started. So when we're talking about data center bridging, we're really talking about a lossless network versus a lossy network. So a lossy network is the typical network that the vast majority of us access on a daily basis. The internet operates on a lossy type network. And this is a lossy network because the protocols themselves, the IP protocols that exist in these networks, are able to actually tolerate packet loss in these networks. So switches will get congested because too many flows will be going into a switch. They'll buffer that traffic, and at some point they'll have to start dropping those packets. And that's a lossy fabric. The vast majority of networks that we access operate on that. The internet works really great that way. So it's multiple architectures are supported, of course, because it's really just an IP network. Now, this is actually a data center network that we're looking at here that has a spine and leaf fabric, and of course this is a lossy network also. However, in data centers have typically and traditionally have had a completely separate side-by-side storage fabric, which consists of a lossless fabric. So this is a fabric that ensures that packets, that when they get sent from the host and they get sent to the target array at the other end, that there won't be any packet loss whatsoever. These types of environments are very sensitive to latency, IOPS, performance, and reliability. And these types of environments have traditionally been built using fiber channel technology, InfiniBand technology, and even FCOE technology. So this is fiber channel over an Ethernet type fabric. However, more and more common nowadays, we're seeing iSCSI fabrics, but also really it's RoCE fabrics and NVMe over fabrics. So this is non-volatile memory express over fabrics and RDMA over converged Ethernet over fabrics. These two top protocols actually work over an IP Ethernet fabric, and DCB is the protocol suite that enables these protocols to work. So this does give the purchasers a story about how they can actually leverage this existing network that they already have, this IP Ethernet network, and using the DCB protocols, they can simply converge these networks into a single network. So this would be a converged network where we have both lossy traffic and both lossless traffic on the network. Another growing popular thing with in storage environments is with the rise of all-flash storage arrays and how they're getting cheaper and cheaper. This is helping to drive the RoCE, the RDMA over converged Ethernet, as well as NVMe Express over fabric type solutions. And so a lot of these solutions are upgrading their storage network to an IP Ethernet storage network, and this will provide the lossless network for these types of solutions too. When we're looking at data center bridging, it's really a suite of protocols. So like I said, this is a suite of protocols that really helps us enhance Ethernet by literally guaranteeing lossless traffic on the Ethernet. So this is when we're talking about how it unifies and enables a unified network. This will also be referred to as a converged enhanced Ethernet network. So of course this is a type of network where both lossless and LAN traffic use the same infrastructure, and of course it has that selling point of how easily it can reduce the cost not having to have these completely separate networks. When we're looking at the components of data center bridging, so the top four on the left here are actually the protocols within the data center bridging protocol suite. DCBX is a data center bridging exchange protocol I'll discuss, and then priority flow control is PFC, so that's priority based flow control. And then we have enhanced transmission selection, which is ETS. And at the bottom we have quantized congestion notification. So I'll just start with that one, saying that this is a layer 2 only protocol. It's a congestion notification protocol that when congestion occurs on the network, it sends a packet back, or it sends the packet on, but it informs the initiators and target that there's congestion. and the initiator and target will throttle back traffic, but it's literally only works at layer 2, and so it's very ever rarely used. I've actually never seen it used. The three main protocols that we're using when we're talking about DCB protocols within the data center is the DCBX, PFC, and ETS. Another one that's really critical though, and this is required for those RDMA and those NVMe over fabric solutions, is IP ECN. So this is explicit congestion notification. This is a layer 3 congestion notification protocol. It works really well at helping to reduce the amount of pause frames that get sent because it can tell the top talkers on the network to slow down their talking so other traffic can get in there. So that's a really critical one that's required for RDMA and NVMe over fabrics. And then finally at the bottom we have a couple other components that are critical within these solutions. The APP, or the application TLV, is a TLV that's enabled by the DCBX protocol. And then of course these types of networks will rely on a CNA in the server. So this is a converged network adapter, and this is a network adapter that will support both Ethernet as well as the protocols within the DCB suite to enable the lossless traffic on the Ethernet. So from here we can see the stack, the OSI stack, and how these different storage protocols access the stack. So fiber channel protocol and InfiniBand leverage are really lightweight protocols. They of course have their own stack. We're really dealing on the Aruba side with the IP Ethernet stack on the right. FCOE has been deployed for a while, however it really hasn't gotten a lot of adoption. Our focus is more on the iSCSI, Rocky, and the NVMe over Fabric solutions, and we can see that they all leverage the TCP and the IP and the Ethernet stack. So let's start talking about the actual protocols. So if we start talking about the protocols, let's start with Ethernet flow control. So this is a protocol that's existed for as long as we've probably known switches, except this is a port-based protocol. So this literally pauses, it tells the sender to pause all traffic on the link. So if that's what you want, if you want to pause all traffic on the link, it works really, really well. But of course that pauses, in a lot of cases in these conversion environments, that pauses traffic that you don't care about if there's packet drops in it. And so PFC is the enhancement to that. This is priority-based flow control. It's really just a simple enhancement to that standard Ethernet flow control. However, now we can actually apply this flow control to a specific queue on an individual port. So each port will have 8 queues, and we can tell in this example, port Q4 has been applied the no pause frame, and so when congestion occurs, a pause frame will be sent into Q4 only. All the other traffic can be treated just like any other traffic, and it can be tail dropped as needed. Now PFC does use the 802.1p priority, so when we're talking about that, we need to ensure that we have a VLAN tag that has this packet tagged with the PFC no drop end to end, from leaf to core to rack to the other leaf. Enhanced transmission selection. So this is the protocol that allows us to ensure that each different type of traffic class on this switch, whether it's lossless or lossy, we can tell the interface on these converged type interfaces that this type of traffic requires or is guaranteed this minimum amount of bandwidth. It's important to note that if another class of traffic is not using their bandwidth, it does not mean that other types of traffic cannot use that. This is just a minimum bandwidth. And of course, the way we use the scheduling mechanism for each of the queues within an ETS solution is going to be based on the specific switch that you have. Strict priority is going to be supported on all of them in Q7. And then the other queues we can apply either DWRR or weighted fair queuing on the 8400. So DWRR is on the 8325s. So again, when we're talking about enhanced transmission selection, this is what actually controls the bandwidth with each of the queues used within that interface that's connected to the CNA or connected to other switches. We do need to leverage that 802.1p priority to assign these classes. By default though, every class is already assigned to one queue. When we're implementing ETS, we're implementing this through the .1p to the local precedence quality of service map configuration, and we're also leveraging the schedule profiles. So when we do the quality of service, the .1p to local precedence map, this is a map that tells the switch which type of traffic goes into which queue, and that's a map that's configurable globally. And then when we do the schedule profiles, this is when we're telling each port how much bandwidth each of the queues can get. This, of course, is a schedule profile that you can create and apply to individual ports. In fact, we have an example of both of those right here. So here on the left, we can see that the quality of service, the 802.1p to local priority, or the CoS map, has been configured so that this switch basically has two queues now. So all the traffic that's marked with a 802.1p priority of 4 is going to go into Q1. That's going to be their iSCSI queue. All the other traffic on this switch is going into Q0. And so now it's basically a two-queue switch, and by using the QoS schedule profile, we can configure the various scheduling mechanism that we're going to use in the various queues on that port. So in this example here, we're using strict priority for Q7, control plane stuff. And then we're telling it Q4 is going to get 60% of the bandwidth and Q0 will get 40% of the bandwidth. Now the other queues have a 1 next to them, but of course we're not going to be having any traffic in those queues, and so they won't take any of the cycles within the weight calculations. So data center bridging exchange, this is the next protocol. This is a really cool protocol that helps us networking guys because it configures the attached servers, the initiators and targets for us. So if the server, the initiator target has a CNA installed and the willing bit is turned on, and the CNA willing bits are usually turned on by default, then when we go through the previous configurations that I spoke about, the PFC and the ETS configurations, those configurations will get communicated down to that attached device, the initiator or the target, and it'll automatically configure that CNA. So when that CNA sends the traffic to my switch, it'll automatically be marked with the VLAN tag. And of course, it'll understand how much of the bandwidth on that link belongs to lossless traffic versus lossy traffic. And so data center bridging is actually a really simple protocol. It's really just an extension of LLDP. So we literally just enable the DCBX TLVs. There's a handful of TLVs that get added when we enable or when we turn on DCBX LLDP. And one of those TLVs is the application TLV. And this is a really important TLV, which is the TLV that's used to actually tell the other switch how to mark the traffic. So in this example here at the bottom here, we're telling the switch, send us all of your iSCSI traffic with a TCP destination port of 3260. That's how we're going to select the traffic. And we're going to tell it, when you send it to us, mark it with a 802.1p value of 4, for example. So as a summary, when we're configuring this solution, it's an end-to-end, these lossless-based solutions are end-to-end solutions. So you need to have an initiator and a target that supports this solution. And when we're deploying this solution, we're going to configure ETS on any of the interfaces that is a converged interface that carries both lossless and lossy traffic. We're going to configure PFC, so that's the no drop queue, and we're going to configure that again on any interface that requires lossless traffic. DCBX will actually be configured on any of the interfaces facing the initiators or targets. And of course, within the DCBX protocol suite, we'll configure that application TLV to tell the attached server how to mark this traffic. So when we're talking about data center bridging solutions with the 10.4 release with Aruba, data center bridging, PFC, ETS, and DCBX are all supported on the Aruba 8325 and the 8400 switch series. Because we don't yet support IP-ECN, we cannot say that we support the Rocky solutions or the NVMe over Fabric solutions. We can support lossless iSCSI solutions. These types of solutions are going to generally require jumbo frames end to end. We usually recommend maxing them out However, depending on the application and how the server and the initiator and target are configured, those admins may want you to reduce that. But we generally start at maximum jumbo frames. So let's talk about configuring data center bridging on these CX switches. So when we're configuring data center bridging, let's start by doing DCBX. And this is quite literally just enabling LLDP, which is enabled by default, and then just enabling the DCBX LLDP. And you can do this globally. As seen here on this screen, you can actually do that at the interface level. And on this screen, we're actually showing how to enable PFC. So we can go into the interface that I don't want any traffic to be dropped on. I can enable LLDP, DCBX, and then I can enable flow control, and I can tell it which queue I want flow control to be applied to. Now, because this does use the 802.1p priority, we are going to need to QoS trust. So we're going to need to make sure that we trust class of service. So these are some quick examples of the show DCBX interface command, which is a really helpful command for DCBX. On the left here, we can see that DCBX has been enabled and that it's active. And on the right here, we can see that PFC, using that same command, is active, and also we can see which queue PFC has been enabled for. Now, this is about configuring the DCBX application configuration. So this is, we have a couple examples at the bottom. So we have mapping iSCSI traffic to priority 4. We can simply do the command globally. So this is a global command. DCBX application, and then iSCSI priority 4. So all iSCSI traffic, mark it with a priority of 4. The example below that is using a common TCP port, but it's the same type of configuration. You can see how easy it is to select your traffic and then remark it how you need it. And then going back to that same show DCBX interface command, we can also see those two previous application TLVs and how they were created and where you can see them. And then finally, we would configure ETS. Now, when we think about configuring ETS, we should think of a few steps. So first, we want to think about the class of service to local priority mapping. And this is required even because we've configured PFC. This is where we're going to configure the switch to tell it which .p priorities go to which queue. Continuing on for ETS, we would then create a schedule profile, which is a global command. And when we do that, we would configure the different scheduling methods as well as the weights. And then we simply apply that to the interface and then just verify it using that view command. So let's go through those quick 5 steps. So this is where we're creating a class of service to local priority mapping. We can see here on the bottom, quality of service, class of service map, anything marked with an 802.1p value of 4. I want you to go into the local priority queue of 1, and let's just go ahead and name that iSCSI. And then, of course, we're going to create a schedule profile. So this is a global command, so QoS schedule profile, and just give it a name. This is an example called my profile. And now that we're configuring this schedule profile, you can see here on the bottom, now is when we're going to start configuring it for the weights for the queue. So now that I'm within the my schedule context is where I'll start telling it which queues get which weight and what scheduling mechanism to use. Like I mentioned, strict priority is supported on Q7, and then the 8325 supports DWRR, and then the 8400 supports weighted fair queuing. With this configuration, Q0 is going to get 40% of the bandwidth, and Q4 is going to get 60% of the available bandwidth. And then we go to the actual interface and we want to apply that. So down here we can see we've gone into the interface context and we can apply the QoS schedule profile, my schedule. And here's a great view showing the quality of service, class of service map, the 2 queues showing the 802.1p code points and which queue they're mapped to, and then of course the schedule profile and how the scheduling has been configured. So in summary, data center bridging is really a suite of protocols, and they were designed to help us ensure that we can create a lossless IP Ethernet fabric. And those protocols primarily consist of DCBX, PFC, and ETS. However, they work closely in these modern Rocky type or NVMe type solutions with IPECN. So keep that in mind. If you are presented with a DCB opportunity, make sure that you understand the application and the solution involved and what's required of the network. Thank you.